introduction and going up to the introduction, and happy to see everyone here. Right. So the title of my talk today is a plan-inspired revolving robot drone with efficient hover flight. So I decided. The introduction. So I'm talking about slightly larger robots here and flying robots. And what I'm showing you is the videos taken from two recent papers from also side robotics. As you can see, they're videos of swarm of quadcopters, right, flying through dense forest. This work is from Chichen University. It's very impressive. And also on the right-hand side is another paper from Caltech using neural network control in order to fly this quadcopter through like very aggressive maneuver or to deal with disturbances. Right? Now, there are lots of things going on and lots of progress has been made in terms of control, perception, navigation, and planning on these flying robots that are probably kind of at the size of your laptop or something. Now, and if you were here in this morning, you will probably have seen also a talk on Barrel, and also Kevin Chen will be presenting later. And on a slightly smaller scale, we're talking about insect scales. There's also, for example, Alpha bees that fly very differently from the quadcopters you've seen just before, right? They can also, for example, deal with disturbances or withstand collisions or impacts from the environment. But the point I'm showing you in two videos is I want to also talk about the power autonomy. Right? So this robot, you can see, they catered, unlike the version that I showed this morning that was actually relying on the solar power that could achieve a short flight. They still catered. They cannot carry on board the batteries, microcontrollers, computing unit, or even sensory devices. So it still also rely on motion capture system for feedback. But so the difference between these two, okay, can be, these two types of robot can be actually understood, okay, by looking at this plot, which is a paper from Dario and Robert, published in Nature in 2016, if I got it right, okay. It's a plot showing flight time versus mass of small robots. Right? And the trend you can see here is very clear. The smaller, the lighter the robots, the shorter the flight time. Right? When you get down to say 10 grams, you can barely fly for a few minutes, and of course below that, you probably don't have power autonomy, so you don't actually have flight time. Right? It's not really a problem for larger robots, and things are getting better, but it's still quite a challenge. And there are lots of reasons behind this. But one reason that it's harder for smaller robots to get power autonomy is also because of the aerodynamic efficiency, right? Which is characterized by Reynolds number. If you are in the field of flying robots, you might be very familiar. If not, that's okay, right? Reynolds numbers, of course, if you work on micro robots, you know this very well. So Reynolds number is basically a ratio, proportion of inertial forces over viscous forces. Right? So as smaller robots or smaller flyers, they have lower Reynolds numbers because the inertial effect becomes less important than the frictional forces or viscous forces, meaning that force becomes dominant, and basically you're going to be losing lots of energy to the environment, to the air. So everything, like lots of energy, is wasted. That's why it becomes less efficient. And you can see Reynolds number of different flyers, right, across different scales. are very different. So smaller robots are not efficient flyers, and that's why we see that reason. Now, apart from this though, or because of this, we can also come back to take a look at this plot again. Apart from the trend that I pointed out earlier, you could also see, right, if I highlight, right, the separation between two types of flyers, and now I'm focusing on the scale between 10 grams to 100 grams, right? So let's talk about something larger first, quadcopters. You know that quadcopters can go to even human scale, but smaller quadcopters, probably a few hundred grams. Right now, lots of DJI stuff probably are down to 200 grams. But the smallest ones that are prevalently used are down to about 30 grams. And they don't make it smaller than that for the reason that it does work very well. Not only the aerodynamic efficiency, but also other scaling effects affecting the efficiency of DC motors, for example. Right. On the other hand, if you look at flying wing robots, right, they are present from up to even below 10 grams and up to 50 grams, 30 grams. Right? They fly very differently. They fly by their wings. And as you can see here, on the same scale, on the same mass, they seem to be actually more efficient than rotorcraft. Right? This is, of course, that lots of explanations, right? It's rather complicated. But simplistically, I can nail this down to two important factors. Right? The first one is about how, the first one, is about the Reynolds number, but, and the mode of lift generation or thrust generation. The motion of flapping wings, which is immediately insects, actually helps improving the aerodynamic efficiency by using what they call unsteady aerodynamics. And I'm going to come back to this, right? The second thing I'm going to mention first is the size of the aerodynamic surfaces. As you can see, these wings, the flapping wings, basically, they are larger compared to small propellers. Right? They cover more area, but their spin or their flap, the motion is slower. So according to one simplistic model, which is momentum theory, when we want to characterize the efficiency of flyers, we can look at power loading. Power loading means the ratio of the lift the mechanism generates over to the power input. Right? This momentum theory is actually rather simplistic. It doesn't actually take into account Reynolds number or that efficiency in that aspect. But momentum theory gives you the result saying that this power loading is proportional to the inverse of the square root of this loading, which is the ratio of lift to the wing area or this area. Right? Now, what I want to mention though is this power loading, as I said, doesn't take into account Reynolds number. So this relationship is momentum theory analysis. So this the application of this equation applies probably to robots of the same mass, same thrust. Okay, it doesn't apply to different scales. So what I mean by that is this. So if I plot out, if I consolidate some data, and I plot out the relationship between this loading and mass, you can see here it's pretty clear. Larger robot has heavier robots have higher this loading, and this can be explained as simple scaling law. This loading is weight of the robot over area, so you expect it to scale proportionally with weight scales with length. Length square cube, area is length cube, and then area is length square. So overall, to scale with the length, right? So larger robots have larger this loading, though it doesn't mean they're more efficient. Now, in the meantime, I'm going to go through this plot a little bit. So at the higher end, this plot go to a wide range of scales. We're talking about planes, quadcopters, right? And then flapping wing robots. you can see this plot here is actually consistent with the momentum theory equation earlier, saying that, I mean, not consistent, but what I'm saying is, if you look at the same scale of hummingbird flight or flapping wing robots at the same scale as quadcopter here, the hummingbird robot have lower disloading, meaning they expected to be more efficient if we're talking about the same mass, right? Now we can go down to fruit flies, and then that one point at the bottom, that's something that has extremely low disloading. That's actually maple seeds. Great. So, but not only that.
You're disconnected from.
Sorry, I'm disconnected from Zoom. My internet is not stable because it's on Wi-Fi.
Don't you dare unplug that. Why don't we just point the camera towards the screen?
Oh,
You disconnect. Just disconnect from Zoom.
okay. Try to use my laptop. Yeah.
You're back.
I'm back.
Yeah.
Ah, nice. Okay, thank you. So that's another thing I want to talk about maple seeds though. So there's this paper, right, from Lenting, which was actually a cover of science from 2009, right? So another interesting fact about maple seeds is that how it generates lift by spinning and rotating and falling while spinning is that it also uses unsteady aerodynamics or unsteady aerodynamics, which actually is the same thing that is shared by flapping wing insects. It's the same thing, right? So the way it works is that for most airfoils or planes, you probably have heard of the word angle of attack, or the angle where the incoming air incident with the wings, right? Make contact with the wings, right? So most of the time we're talking about lift coefficient, meaning how much lift is generated by the air. Now, for most airfoils or wings, the lift coefficient becomes very small when the angle of attack is large, right? Or the wing pitch angle is high. It's not the case for insect wings, which is flapping at very high angle, and it is not in the case for maple seed wings, right? So it actually makes the flight at smaller scale, our low Reynolds numbers, more efficient. So taking this into account, we kind of were motivated to make a robot that uses first large wings in order to generate lift, and generate the lift by spinning or by rotation. Second, the wings are actually going to be operating at relatively large angle of attack, and it doesn't stall because it's going to be using steady aerodynamics, just like how insects fly, right? So the robot here, as you can see, the two large wings, there are only two actuators, which are basically two small motor-driven propellers. The robot here is 35 grams, which is not huge, I mean, big compared to 80 milligrams. However, the size of this robot is actually huge. It's actually about 60 centimeters. So each wing is about 30 centimeters in length. Right. So I'm showing you kind of a quick video of how it works. So this is when the robot is flying. You can see it's spinning, right? So the highlight or working principle here is very simple, unlike vertical rotorcraft, where it's you're using the propellers to generate lift directly. We have two propellers that are pointed horizontally to make the robot rotate. And then by the rotation, it's the wings that is actually responsible for generating the upward motion or to keep the robot aloft. Right. So we wanted to make a very efficient robot based on this. Right. So how to actually design or make this work properly, we can also come back to take a look how this works, right? From the power loading standpoint, meaning how much if you have to generate and then how much power is going to consume. So the lifts are generated by the wings, and the power input is the power that goes into the two motors. Right? When it's spinning, the lift is generated as a function of the rotational speed, quadratic function of rotational speed, governed by the lift coefficient Ct, which is depending on the wing profile, and power is of course current times voltage that you use to drive the actuators or the motors in this case, right? So putting everything together, right? When the wing is generated, it's rotating at angular velocity omega. Of course, it's going to be generating counter torque, which is drag. Right. So together, the thrust balance generated by the propeller, of course, depends on the voltage, but also depends voltage of the motor, but also it actually also depends on how fast the propeller is moving or omega as well. So putting everything together, we can write a function of power loading of the robot to be a function of the weight of the robot and thrust and torque coefficients of the wings, which depends on the wing profile. So our job here, right, is to actually find the wing profile or configuration of the robot that maximizes the power loading to make the robot efficient. It's a model-based optimization that we could actually test a few wings, and then we fit the model, do parametric search, and also identify the model of the motors. Putting everything together, right? What we could achieve, right, with this robot is that with a small battery, 215 mAh, the robot is 35 grams, can fly for 15 minutes. Or if we equip the robot with a slightly larger battery, the robot would weigh 42 grams, but it can fly for 24 minutes, right? Which actually doesn't sound that great, but you have to take into account or keep in mind that the robot is only 40 grams. So the flight time, for example, in comparison of a quadcopter of the same size, would be about a half of that. Okay? But based on our test and also from commercial quadcopters as well. Right? Now, with the ability to fly, okay, I can come back, right, to look at flight time, okay, of small robots that we collected. You can see here the stars A and B, the flight times roughly twice of other robots, and in terms of power loading or power consumption, is also about a half of other robots. Now, so coming back here to, and the reason behind that can be explained by coming back here, right? When we put our robots onto this part of this loading, our robot has this loading of 1 order of magnitude lower than flapping wing robots or other previously developed Samurai or Maple City inspired robots, and also 2 orders of magnitude lower than quadcopters. So one interesting thing is we can also do flight control, meaning we can move the robot to follow or track a trajectory. And the one thing is to do this is a little bit slightly different from quadcopters or flapping wing robots, because for quadcopters or flapping wing robots, the lift is always generated in the upward direction, right? So you have to regulate or manipulate the attitude, the orientation of the robot for the robot to create lateral acceleration. For our robot, we can actually use thrust from the propeller, which is pointed horizontally, to move the robot sideways directly by timing how to actuate that propellers, right? So despite having two actuators, we can still do 3D position tracking following a trajectory. The precision, I'm gonna admit it's not the best, but it is very durable, and I'm gonna feed forward to it. And skip that video for a little bit. So the rotation, though, I always get asked the question. So if the robot keeps rotating, then how is that going to be useful, right? Though I mean, thinking outside of the box, you can also see that, for example, LiDAR sensors, they work by rotation already. So if you just put sensors, for example, time-of-flight sensors onto the robot, keeps rotating, then you can construct the map of the surroundings directly. And even that, honestly, some people weren't happy, so we also had to put a camera on the robot to show that by timing the shutter speed, by sync the shutter speed or timing shutter speed with the rotation, you can also get kind of low resolution video. And this is a very simple implementation. We just got Arduino camera and put it on, and we didn't think too much. And this is because, and actually at the time I wasn't very happy with my student because he got like this 20-gram camera Arduino setup. I thought that's very heavy, but it turns out the robot could carry that fine, despite the fact that the weight of the robot was only 35 grams, so the payload of the robot is actually 20, right, in the end. So I'm gonna say basically that's one of a few examples. So I'm gonna show you a quick kind of spin-off work from this paper, which also has been recently published in TMED. Right? So we show that a robot with two actuators can fly, and so we thought of doing something else as well, right? By looking at quadcopters and looking at bicopters. And I'm not gonna lie that previously there have been attempts, right, to use robots or quadcopters or rotorcraft with less than 4 propellers, fine, and they have done a really good job, one on trajectory tracking, and the other one also using onboard vision for stabilization. So what I'm presenting here, what I'm showing here is basically something on a slightly different aspect. So we were thinking of in terms of modular system, where if you have a robot with a rotorcraft with 2 propellers, you can fly while spinning. But on the other hand, right, if we have 4 propellers, then it means that we can treat it as a quadcopter. But then we can also split that into 2 bicopters and fly differently during flight. Okay, right. So I think basically that's where I'm gonna wrap up my talk. So I would like to thank my students, collaborators, and of course my funding grant. So the first author of the work is Song Nanbai, my undergraduate student who's graduating soon. So again, okay, thank you. I'll be happy to take questions.
Very wonderful talk. And as someone who works on flying insect robots, I really like your overview on the challenges in getting the power autonomy in the insect state robots. So to that end, I have a couple of questions. So first,
Sure.
like, how do you think is the scalability of this concept, even at a smaller scale? Like, I guess since you're using motors for providing power to the robot, scaling down motors is obviously not the best thing to do, but do you have a solution to that impact?
Yes, good question. So how does the scaling work? I would actually see that it could scale down. The limitation is about actuation. So because motors smaller than this won't be very efficient. But of course, if we could actually actuate it with other types of actuators that work better at small scales. I don't see why not. And of course, real maple seeds are actually way smaller than this, right? So you're right. It's probably that it can it scale up? That I think so, but the efficiency might not be as great because of the Reynolds numbers. When you scale up the Reynolds number larger, you cannot use unsteady aerodynamics. It would be good, but it probably won't be much superior than other platforms.
Yeah. And the second question that I had was like, do you think like adding additional degrees of freedom in controlling the angle of attack thing would improve your control operating?
Yes, good question. So I also have to mention that there's another, to be fair, right? There's another group from SUTD, Singapore University of Technology and Design, who has done larger prototypes, and they have done quite a number of, they have published quite a number of papers that they also have control of the angles of attack of the wings. So it would actually help with the performance for other purposes. But focusing on small scales, if we want to say save the energy and make things small and light, we just want to throw away everything that's not needed.
Yeah.
Thank you.
So, yeah, very nice work. I
Thank
just
you.
was wondering for the control. Am I understanding right that you change the duty cycle, you change the lift from right to left so that you can do the control of that? Is that the way it works?
You are certainly correct. So I simplified my explanation. The most simplified model is basically you're not changing the lift of the wings.
But the speed so that you have inclination and that's the way it works.
So that would work, but what we're doing right now is mostly using the horizontal thrust directly. So for example, when the robot is in this orientation, if you reduce this thrust and increase this thrust, then you get horizontal acceleration directly without actually tilting the robot.
Choose the orientation, you have to change the duty cycle by your turn, basically, right?
That's correct. That's
And
correct.
when you lower the speed, for example, one propeller, you would have an inclination and you could keep and make controlling this way.
I think so, but I would believe that it would require more actuators to achieve that, to control the.
No, I mean only the speed. That's the only thing you control, right? The speed.
That's right now.
Well,
It
yeah,
is. Yes.
Thank you.
Thank you. Yeah.
Okay, let's thank our speaker one more time.